In this video, we're looking at another application of the derivative called linear approximations. So basically what we're doing is we're drawing the tangent line to a curve at a particular point. So in this case, we have f of x is 1 over x, and we have our tangent line drawn to the curve at the point x equals 2. And you can see if you zoom in a whole lot, so the graph on the right is basically the graph zoomed in a considerable amount. And you can see that if we zoom in a lot, the tangent line actually is a really great approximation for the graph, really close to 2, right? So really close to 2, that at 2 the tangent line touches the curve, but close to 2 the tangent line approximates the value of the curve very well. And you can see as you move further and further away, you can see this distance between the tangent line and the actual curve become further, don't they? So that's what linear approximations are. They're also called linearizations, and we can use the tangent line as a linear approximation. So what we want to do here is we want to come up with the equation of the tangent line. We're going to use the tangent line to make the approximation. So we need an equation for that tangent line. And so if you recall, this was the formula for the equation of the tangent line. Hopefully you could do it without the formula just by using the slope and a point, right? But if you need the equation, there it is. And so our a value in this case is 9. We're going to find the equation of the tangent line at point A, which in this case is 9. So a equals 9. Our f of x is the square root of x. And since we're going to need f prime of a, I'm going to go ahead and find f prime of x right away. So let's rewrite f of x as x to the 1/2. So f prime of x is equal to 1/2 x to the negative 1/2. And remember, this can be rewritten as I can bring the x down to the denominator to make it positive, so it's 1 over 2 times x to the 1/2, which is equal to 1 over 2 root x. All right, so that's my derivative. And to find the slope of the tangent line, it's just y equals f of a, and f of a is f of 9, which is the square root of 9, which is 3. So we have 3 here, plus f prime of a, and f prime of a is f prime of 9, which is equal to 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 6. So we have 1/6 here, times x minus 9. All right, so a lot of times people want to simplify this to get it into the form y equals mx plus b, but there's really no need, and in fact, I encourage you to leave it in this form, and you'll see why it actually helps us to leave it in this form. So we want to use the equation of the tangent line to approximate the square root of 9.1. So let me remind you again what we're looking at here. We have the graph for y equals the square root of x. We know what the square root of 9 is, but we can use the tangent line to approximate the square root of other values that are super close to 9. We're using the tangent line, the equation of the tangent line, to approximate other values that are super close to 9. So if we want to approximate the square root of 9.1, we just use the tangent line here. And so we can plug in 9.1 for x. So we get 9.1 minus 9. And so you get 3 plus 1/6 times 9.1 minus 9 is 0.1, right? And we can write 0.1 as 1/10. So we get 3 plus 1/60th. And if you want to, you can calculate that. And let me see what we get. All right, so I get 3.0166, and the 6 continues. Okay, so that's our approximation for the square root of 9.1. Notice that if we didn't have a calculator that had a square root button, we could still calculate the square root of 9.1 just by using linear approximations. And in the old days, they did this because they didn't have calculators. Okay, so let's actually find the value of the square root of 9.1 with our calculator. So if I take 9.1 and I take the square root of it, I get 9.1, and the square root of that is 3.0166. So the actual, this is an approximation, right? So the square root of 9.1 is approximately 3.0166, like this. And the square root of 9.1 on the calculator is 3.0166206 is what I get. So hopefully you can see the value that we got with the linear approximation is actually very accurate and accurate to four places. And so linear approximations, again, if we stay very close to the value of A, and in this case our A was 9, are very good.